NASA's James Webb Space Telescope found something it was never supposed to find. Not a planet, not a star, something that shouldn't exist. Not according to the laws of physics that have governed every cosmological model since Einstein. And the scientists who discovered it didn't celebrate.
They went quiet. Because if what Webb detected is real, if the data holds, then everything we thought we knew about how the universe began, how it aged, and how it will end may be wrong. Not slightly off, not in need of minor correction, fundamentally broken. And here's what makes it worse. This isn't the first time the universe has sent us a message we couldn't read. In the 1990s, two rival teams of astronomers set out to prove a theory about the universe's death. What they found instead won them the Nobel Prize and shattered 3 centuries of physics. History is repeating itself. Only this time, the anomaly is bigger, the implications are darker, and the universe may be telling us something about our place in it that we are not ready to hear. Let's start with what you need to understand about how we look at space. When you look at the night sky, you are not seeing the universe as it is. You're seeing it as it was. Light travels at a finite speed, roughly 300,000 kilometers per second. Fast, yes.
But the universe is incomprehensibly vast. The light arriving at your eyes from the Andromeda Galaxy left its source too, 5 million years ago, before modern humans existed, before language, before fire. The James Webb Space Telescope pushes this further, dramatically further. Webb doesn't just observe deep space, it observes deep time. It can detect light from galaxies that formed when the universe was less than 400 million years old. To put that in context, the universe is 8 billion years old. Webb is looking at its infancy.
And it is in that infancy, in those first fragile moments of cosmic existence, that Webb found something that forced astronomers to stop and ask a question no one wanted to ask. What if the universe is older than we think? Or worse, what if it isn't old enough to contain what we're seeing? The galaxies Webb detected in 2023 and early 2024 are not just surprising. They are too massive, too structured, too evolved to exist this early in cosmic history. They look like galaxies that should have taken billions of years to form. And yet there they are, fully assembled, just 500 million years after the Big Bang. The universe, apparently, didn't get the memo. To understand why this is so alarming, you need to go back to 1998. 2 teams of astrophysicists were competing to answer one of cosmology's oldest questions. Is the universe expanding, slowing down, and eventually going to collapse back on itself, the so-called Big Crunch? Or is it expanding at a constant rate, heading toward a cold, dark, infinite death? Both teams were expected to prove one of these 2 outcomes. What they found instead stopped both teams cold. The universe wasn't slowing down, it was accelerating. Some invisible, undetectable, deeply mysterious force was pushing space itself apart at an ever-increasing rate. They called it dark energy. And in 2011, Saul Perlmutter, Brian Schmidt, and Adam Riess received the Nobel Prize in Physics for discovering it. But here's what rarely gets told in the popular version of that story. When Schmidt's team first saw the data, when the numbers came back showing acceleration, Schmidt himself thought there was a mistake. He described the moment as feeling like he had been told he'd thrown a ball into the air and it had flown faster the higher it went. Not just counterintuitive.
Physically impossible by everything he knew. He spent months looking for the error. There was no error. That discovery forced a complete reconstruction of the standard model of cosmology.
Scientists had to insert a new parameter, the cosmological constant, and admit that roughly 68% of the universe is made of something they cannot see, detect, or explain. We went from thinking we understood the universe to realizing we only understand 5% of it.
Now with Webb, history is threatening to repeat itself, with even higher stakes.
Astronomer Garth Illingworth, one of the architects of the Hubble Deep Field program that first showed humanity how many galaxies exist, reviewed Webb's early deep field data and made a statement that lingered in the astrophysics community. We were just not anticipating finding things this bright this early. That word, bright, matters more than its. Brightness in this context means mass, means structure, means age. What Webb was seeing was not supposed to be there. And the question that follows, the one that keeps cosmologists awake, is not how these galaxies formed so fast. It's what had to be wrong in our model to miss them entirely. Here is where the physics becomes genuinely unsettling. The current model of galaxy formation, the Lambda-CDM model, is the most successful cosmological framework ever constructed.
It accurately predicts the large-scale structure of the universe, the distribution of galaxies, and the formation of dark matter halos. It has survived decades of observational testing, but it has a speed limit. According to Lambda-CDM, galaxies don't appear fully formed. They grow, gas clouds collapse under gravity, stars ignite, smaller galaxies merge into large ones over hundreds of millions, sometimes billions of years. The process is slow, sequential, and hierarchical. Think of it this way. You cannot build a skyscraper overnight. You pour foundation, you frame floors.
You wire and plumb and enclose, layer by layer. The Lambda-CDM model is the building code of the universe, and Webb is finding skyscrapers where the concrete shouldn't even be dry yet.
In 2023, a team led by astronomer Ivo Labbé published a paper in Nature describing 6 massive galaxies observed by Webb that existed just 500 to 700 million years after the Big Bang. These galaxies contained as many stars as the Milky Way contains today. Some were even larger.
The Milky Way took 13 billion years to build itself. These galaxies appear to have done it in a fraction of that time. Labbé's team ran the numbers. If these observations are confirmed, if they're not artifacts of Webb's instruments or errors in redshift measurement, then the total mass in stars in the early universe is up to 100 times greater than Lambda-CDM predicts. 100 times, not a 10% error, not a calibration issue. A 10,000% discrepancy between prediction and reality. When Labbé was asked about this publicly, he said something that belongs in a different kind of conversation. Not a scientific paper, but a philosophy seminar. We've found something that shouldn't exist.
And we don't know what to do with it yet. There are 3 possible explanations, and only one of them leaves our understanding of the universe intact. The others require us to rewrite the opening chapter of cosmic history, and possibly the final one too.
Science, at its edges, is not a cold discipline. It is deeply uncomfortably human. Because the people doing this work, the ones staring at Webb's data at 2 a.m.,
in Pasadena or Baltimore or Munich, are people who built their careers, their identities, their entire intellectual architecture on a model of the universe that may now be fracturing beneath them. Consider what it means to be a cosmologist in this moment.
You spent 20 years mastering the Lambda-CDM model, you taught it, you published papers refining it, you used it to predict observations that were later confirmed. It worked. Again and again it worked. And now a telescope, the most powerful ever built, is returning images that whisper, maybe not. Astronomer Mike Boylan-Colchin at the University of Texas, one of the researchers analyzing Webb's galaxy data, put it plainly in a way that most scientists would be too cautious to say publicly. If the data is right, we have a very serious problem. That phrase, if the data is right, is carrying enormous weight. Because Webb's instruments have been calibrated with extraordinary precision. Its infrared detectors operate at temperatures near absolute zero. Its mirror segments are aligned to within nanometers. The engineering margins are almost incomprehensible. The hope, the lifeline, is that redshift measurements could be off. Redshift is how astronomers calculate distance and therefore age. The more a galaxy's light stretches toward the red end of the spectrum, the farther away, and the further back in time it sits. If Webb's photometric redshift estimates are slightly miscalibrated, some of these early galaxies might actually be closer and more recent than they appear.
But spectroscopic follow-up observations, the gold standard, the method that removes ambiguity, are beginning to confirm the photometric data. The galaxies are where Webb says they are. There is a particular kind of vertigo that comes with scientific paradigm collapse.
Thomas Kuhn described it in 1962 in The Structure of Scientific Revolutions, the moment when anomalies accumulate to the point where a framework can no longer absorb them. He called it a crisis, not failure, not a catastrophe. Crisis, the necessary, painful, productive moment before a new model is born. Physicists alive today may be standing inside one of those moments right now. And unlike the scientists who discovered dark energy in 1998, this generation has a tool that can keep watching. Webb is not done. It will observe deeper, longer, with more precision, for years. Every new image is either a confirmation of the crisis or a clue toward its resolution. What those clues are beginning to suggest is something that not everyone in the astrophysics community is ready to say out loud. But some are.
Here are the 3 explanations. And here is why each one should stop you cold. Explanation 1. Webb's instruments are producing systematic errors in early galaxy observation. The galaxies aren't as massive as they appear. The model survives. This is the comfortable answer.
It is also the one that spectroscopic confirmations are steadily dismantling. Explanation 2. Lambda-CDM is fundamentally incomplete.
Galaxy formation in the early universe was dramatically faster than the model predicts, perhaps due to dark matter properties we don't understand, or early stellar populations with different characteristics,
or feedback mechanisms that allowed gas to collapse into stars with unprecedented efficiency. This is the scientifically painful answer. It means decades of modeling work require reconstruction. It means the textbooks are wrong, but it leaves the Big Bang intact, the age of the universe intact, and crucially, it leaves us intact.
We are still a species in a universe we can eventually understand. Explanation 3 is the one being whispered in corridors. What if the universe is not 13, 8 billion years old? The age of the universe is calculated using the Hubble constant, a measure of how fast space is expanding.
But for the past decade, 2 independent methods of measuring the Hubble constant have returned different values, consistently, reproducibly. The discrepancy has a name, the Hubble tension, and Webb has made it worse, not better. If the Hubble constant is wrong, if space is expanding at a different rate than we calculated, then our estimate of the universe's age, the universe could be older than 13.8 billion years, old enough for these massive galaxies. Old enough, perhaps, for things to have happened in the universe's history that our models have not accounted for.
cosmologist Catherine Freese at the University of Texas has explored alternative models, including what she calls eternal inflation, in which our observable universe is not the only one, and the Big Bang was not the beginning of everything, but merely a beginning.
One bubble of space-time nucleating inside a vast, eternal frothing sea of possibility. If that's true, then the universe Webb is showing us isn't broken. It's just older and stranger and larger than we ever allowed ourselves to imagine. And we are not at the center of it. We are not at the beginning of it. We are a brief, improbable flicker, watching the edges of something we may never fully see. Here is what we know with certainty tonight. The James Webb Space Telescope has found galaxies that do not fit our model. Multiple independent teams have confirmed them. Follow-up spectroscopy is holding. And the astrophysics community, cautiously, carefully, the way scientists always approach the terrifying, is beginning to accept that something in our cosmological framework must change. What that change looks like, no one knows yet.
But every scientific revolution in history has felt like this at the beginning. Not triumph, not discovery discomfort, the feeling that the map no longer matches the territory. We are cartographers, suddenly aware that an entire continent is missing from our charts, and Webb is still watching.
If you want to understand what the Hubble tension actually means, why two different measurements of the same universe keep returning different answers, and what it might mean for the fate of everything, that's the next video. The numbers don't agree. And the reason why might be the most important unsolved problem in all of science.